Okay, let us now proceed to three-dimensional force system of concurrent forces. Now, you try to recall that a force system is in equilibrium when the resultant force is equal to 0. So, if we try to write the resultant force in Cartesian vector form, your R in here is now equal to the magnitude of Rxi plus we have your Ryj plus we have your Rzk, and the resultant should be equal to 0. So that is the condition of equilibrium. Now in scalar form, your Rx is equal to summation of forces along the x-axis. Since the resultant is equal to 0, then summation of forces along the x is equal to 0. Now, similarly, your Ry is equal to summation of forces along the y. Again, the resultant force is equal to 0, hence summation of forces along the y-axis is equal to 0. Your Rx in here, Rz your Rz is equal to summation of forces along the z-axis. The resultant is equal to 0, hence we have summation of forces along the z-axis is equal to 0. So, the three equations of equilibrium for a three-dimensional force system of concurrent forces are summation of forces along the x-axis is equal to 0, summation of forces along the y-axis is equal to 0, and summation of forces along the z-axis is equal to 0. Okay, for sample problem number 1, the particle shown, so we have a particle shown in here, okay, is in equilibrium under the action of 4 forces on the free body diagram. Now, determine the magnitude and the coordinate direction angles of the unknown force F4. So your F1 in here is 120 pounds. Okay, so you have your X slope is 4 feet. So you have your Y in here is 3 feet. Now your F2 is 250 pounds down along the z-axis. And your F3 is equal to 300 pounds, making an angle of 30 degrees with the y-axis. So we are required to determine the magnitude of F4 and the direction angles of F4. Okay, so first, let us try to determine now the components of F1. So your F1x is now equal to 120 multiply this one by the x slope, which is equal to 4 all over the hypotenuse in there is 5. 4 all over 5, or this is equal to 96 pounds. Now, your F1y is now equal to 120. So we have the y slope which is equal to 3 all over 5, or this is equal to 72 pounds. You try to take note that the y component is going to the left, hence this one in here is negative, and that one is negative. Now, your F1 has no component in the z-axis, and therefore, this one in here is equal to 0. Now, such that in Cartesian vector form, your F1 is now equal to your Fxi plus Fyj plus Fzk. So in Cartesian vector form, your F1 in here is now equal to 96i plus, we now have a minus 72j. It's minus 72j. So let's proceed now to your F2. Okay, so this is now your F1, and let's proceed to F2. Now, let's try to determine now the components of F1, F2 in the x-axis. So, F2x is equal to 0. And your F2y is also equal to 0. And your F2z is equal to negative 250. So, it's equal to negative 250. F2x and F2y, your F2 has no component in the x-axis and in the y-axis because your F2 is directed along the z-axis, and that is going downward. Hence, this one in here is negative 250 pounds. Okay, now in Cartesian vector form, your F2 therefore is now equal to, so we have F2xi plus F2yj plus, we have F2zk. So, in Cartesian vector form, your F2 is the 0, 0, hence we have minus 250k. That is minus 250k. So, for F sub 3, so your F sub 3, so let's try to determine the components of F sub 3. So your F sub 3x is equal to, okay, 0. Okay. And your F3y is equal to F3, and that one is equal to 300 cosine of 30 degrees. You try to take note that F3 is lying on the YZ plane only. And we now have, and this is therefore equal to 300 cosine of 30 degrees. I'm just going to left it there. And your F3Z is equal to, F3 is going to the right, and F3 is going upward in the Z direction. So it is also positive 300 sine of 30 degrees. So it's positive sine of 30 degrees. Hence, your F3 in Cartesian vector form is F3xi plus F3yj plus F3zk. So in Cartesian vector form, F3 is now equal to, so this is 0, so we have 300 cosine of 30 degrees J plus 300 sine of 30 degrees k. So that is now your F3. And for F's of 4, we have to determine now your F4x is unknown. So I say to F4y is also unknown, and F4z is also unknown. Let's then try to apply. So let us try to apply now equations of equilibrium. Okay, so the equations of equilibrium are summation of forces along the x, summation of forces along the y, and summation of forces along the z are equal to 0. So summation of forces along the x is equal to 0. So we have F1x is 96. And then F2x is equal to 0. So in this case, so this is equal to, so you have F1x plus F2x plus F3x plus F4x. So that is equal to 0. So F1x is equal to 96. F2x is equal to 0. F3x is equal to 0. And then we now have your F4x. So let's try to have now plus F4x is equal to 0. Hence, your F4x is equal to negative 96 pounds. What does the negative sign here indicate? So it indicates that this is going back of the origin. The other equation of equilibrium is summation of forces along the y is equal to 0. So so this is now F1y plus F2y plus F3y plus F4y is equal to 0. So we have your F1y is negative 72 pounds. Your F2y in here is equal to 0. And your F3y is equal to, so that is plus 300 cosine of 30 degrees. And then your F4y is known, plus F4y is equal to 0. And therefore, your F4y is equal to negative 187.808 pounds. So this is going left of the origin. And we have summation of forces along the z is equal to 0. So your F1z plus F2z plus F3z plus F4z is equal to 0. So your F1z is equal to 0. Your F2z is equal to negative 250 pounds. Your F3z is equal to 300 sine of 30 degrees plus f for z is equal to 0. Hence, the value of f for z is equal to 100 pounds. So this is 100 pounds. So this is positive, therefore it goes upward. So let us try to determine now the magnitude of F4. So the magnitude of F4 is now equal to the square root of f for x squared plus f for y squared plus f for z squared. So this is therefore equal to the square root of 96 squared plus 187.808 squared plus 100 squared. So the magnitude of F4 is equal to 233.46 426 pounds. So this is pointing backward. So it's pointing backward up to the left. So that is up to the left. Let's try to determine now the direction angles of F4. Okay, so your F4, your theta x in here is equal to the arc cosine. This is equal to the arc cosine of F4x all over F4. So this is equal to the arc cosine. F4x is equal to 96, so that is negative 96 all over f sub 4, which is 233.426 pounds. And therefore, your theta x in here is equal to 114.28 degrees. So that is therefore your theta x. So your theta x, F4 makes an angle of 114.28 degrees with the positive x-axis. And then your theta y is now equal to the arc cosine of F4y all over F4. So that is equal to the arc cosine of F4y is minus 187.808 all over F4. That is 233.426. So that your theta y in here is 143. That is 143.57 degrees. So F4 is making an angle of 143.57 degrees with the positive y-axis. And we now have your theta z is now equal to the arc cosine of F4z all over F4. And this is therefore equal to the arc cosine of F4z, and that one is 100 over 200 133.426. And your theta z is 64.63 degrees. Again, F4 is making an angle of 64.63 degrees with the positive z-axis. Sample problem number 2. A 3,000-pound cylinder is supported by a system of cable as shown. So you have your cable A, we have your cable B, and we now have your cable C. So the weight of the cylinder is equal to, the weight of the cylinder is equal to 3,000 pounds. Determine the tension in cables A, B, and C. So this is the x-axis, the y-axis, and that one is the z-axis. So let us try to consider this part in here as point O, which is the origin of the three cables. Now, let's try to determine now the coordinates of points. So your point O in here, so we have 0, 0, and 0. So that is the origin of the coordinate system. And your point A has a coordinate of, so that's your point A. So we have 4 in the z-axis, so that is positive. And then we have 3 in the y-axis, so it is left of the origin, so we have negative 3. And then in the z-axis, so that is positive 6 going up. And then for point B, so the coordinates of point B is, we now have minus 4, so that is going back. And then your y is minus 6, that is negative 6. And then your z is positive 4. Now, we now have the coordinates of point C. Your x is 0. Your z is along the y-axis. So your y is positive 5. And your z is equal to 0. So, let us start getting now the tension in each cable. Cable A, cable B, and cable C. Let us try to draw the free body diagram of the cylinder. So FBD of the cylinder. So the FBD of the cylinder is so this is the weight of the cylinder. So we have the weight of the cylinder, and this one is equal to 3,000 pounds. We have tension in A, so we have your TA. So this is now the tension in A, cable A. And then we have tension in cable B. So this is therefore the tension in cable B. And we have the tension in cable C. This is TC. Now, knowing now the free body diagram, let's try to determine now the tensions, okay, of cables A, B, and C respectively in Cartesian vector form. So third for TA. So in Cartesian vector form, your TA, okay, so let's try to get TA is now equal to the magnitude of TA, multiply this one by a unit vector in the direction OB. Unit vector in that OA, in the direction OA. So again, your unit vector again is now equal to a position vector all over the magnitude of this position vector. Now, let's try to get first the components of the distance OA. So we have again the x component, we have your y component, and your z component. So in the x, so we have OA, so it is directed, okay, towards A. So it is A minus O. So that is 4 minus 0. That is 4. Then we have minus 3. And that one is negative 3. And then 6. And that is positive 6. Hence, the position vector in here, OA, is now equal to your xi plus yj plus zk. And this is equal to, we have 4i minus 3j plus 6k. The magnitude of this position vector is now equal to the square root of 4 square plus 3 square plus 6 square. And this is equal to the square root of 61. Hence, your TA, Cartesian vector form, is now equal to TA, and then your ROA, so that is 4i minus 3j plus 6k all over the square root of 61. So your TA in here is now equal to, we have 0.512i, 4 over the square root of 61, minus 3 over the square root of 61 is minus 0.384 TA. So we have now your TAI minus 0.384, we have TAJ. Then 6 over the square root of 61 is 0.768 TAK. So that is now your cable TA in Cartesian vector form. Now, so your in scalar form, your TAX is equal to 0.512 TA. And your TAY is equal to negative 0.384 TA. And your TAZ is equal to 0.768 A. Now, for the tension in cable B. So again, your T sub B is now equal to the magnitude of this vector, multiply this one again by a unit vector in the direction OB. Again, NOB is equal to a position vector in the direction OB all over the magnitude of that position vector. So again, let's try to get now the components, okay, of the distance, okay, of the distance OB. Again, we have your X, Y, and your Z. So, this is B minus O. So, we have minus 4, and then minus 6, Y, and your Z is 4. Now we have now your ROB is now equal to minus 4I minus 6J plus 4K. And the magnitude is now equal to the square root of 4 square plus 6 square plus 4 square. And this is therefore equal to the square root of 68. So that is the square root of 68. Hence, we have your T sub B is now equal to the magnitude of the cable B, multiply this one by a unit vector OB. So that is minus 4I minus 6J plus 4K all over the square root of 68. Hence, your TB is now equal to negative 4 over the square root of 68. That is negative 0.485. 0.485 T sub B I minus 6 over the square root of 68. So that is minus 0.728. 0.728. So we have TBJ and then plus 4 over the square root of 68 is 0.485 T sub B, and that is now your K. So this is your tension in cable B in the Cartesian vector form. Now, in scalar form, your TBX is equal to negative 0.485 T sub B. And your TBY is equal to negative 0.728 T sub B. And your TBZ is equal to 0.485 T sub B. Now for tension in cable C. So, the tension in cable C in Cartesian vector form is the magnitude of that tension, multiply this one by a unit vector OC. So again, your unit vector OC is now again a position vector OC all over the magnitude of this position vector. So we have again the components of the distance OC. Your X, you have your Y, and your Z. So that is from O to point C, so C minus O. So that one is 0. So we have 5 minus, so that is equal to 5, and then 0 minus 0. That one is equal to 0. Hence, your ROC is now equal to, that is 0. So we have positive 5, that is 5J. And we now have 0 ang Z component. Hence, the magnitude of this is the square root of 5 squared. So that one is equal to 5. Hence, your TC in Cartesian vector form is now equal to the magnitude of this vector by a unit vector. And that unit vector is 5J all over 5, or this is equal to TCJ. So that is equal to TCJ. In scalar form, your TCX is equal to 0. So your TCY is equal to 1. T is equal to TC. TCY is now equal to TC, and your TCJ is equal to 0. For the weight of the cylinder, so this is directed downward. So in Cartesian vector form, so this is equal to minus 3,000 K. So that is along the Z axis. So in here, in scalar, so you have Wx is equal to 0, Wy is equal to 0, and Wz is equal to negative 3,000 pounds. Apply equations of equilibrium. Now, summation of forces along the x-axis is equal to 0. Now, we now have your TAX is equal to, so your TAX is equal to 0.512 TA. So we have 0.512 TA. And your T sub Bx is equal to minus 0.485 T sub B. And your T sub Cx is equal to 0. And Wx is equal to 0. Hence, this one is now equal to 0. So let us consider this one as the first equation. Summation of forces along the y-axis is equal to 0. We have your TAY is negative 0.384. That is TA. And your TBY is negative 0.728 T sub B. And your TCY is equal to TC, so that is plus T sub C. And this is equal to 0. So let's consider this one as the second equation. Next equation of equilibrium is summation of forces along the Z is equal to 0. So we have your TAZ is equal to 0.768. 0.768 TA. Your T sub B, Z is positive 0.485 T sub B. And your TZZ is equal to 0. And then WZ, okay, so your WZ is equal to negative, so that is minus 3,000 pounds is now equal to 0. So minus 3,000 pounds is now equal to 0. So let us try to consider this one as equation 3. From equation 1, if you try to take a look from equation 1, so your T sub B is equal to 0.512 TA all over 0.485. So over 0.485. So let us try to substitute T sub B in equation 3. So if you try to substitute this one in equation 3, then 0.768 we have TA plus 0.485, multiply this one by T sub B, which is 0.512 TA all over 0.485 should be equal to, transpose this to the other side of the equation, and that one is equal to 3,000 pounds. So that is equal to 3,000 pounds. So 0.768 plus this one is equal to 1.28 T sub A is equal to 3,000 pounds. Hence, the tension in cable A is equal to, this is 3,000 over 1.28. And this is therefore equal to 2343. So we have 2343.75 pounds. Now, let us try to determine the tension in cable B. So from this equation, T sub B, which is equal to 0.512 TA. That is 0.512 TA, and the value of TA is 23.75 all over 0.485. Hence, the tension in cable B is equal to 2474. 2474.227 pounds. Now, knowing now the value of TA and TB, let us try to substitute these values in equation 2. So let us try to substitute TA and T sub B in equation 2. So this is your equation number 2. So we have minus 0 minus 0.384. So that is TA. TA is 2343. Is 2343.75 plus minus 0.728. So your T sub B is 2474.227. Okay, I'm going to continue it here. So plus T sub C is equal to 0. Hence, the tension in cable C is equal to 2701.237 pounds. Let's proceed to sample number 3. We have a container of weight W is suspended from ring A. So this is suspended from a ring at point A, to which the cables AC and AE, cable AC and AE are attached. Now, a force P is applied to the end F. Okay, so we have to the end F of a third cable which passes over a pulley at P. So this is now passing over a pulley at point B. So there is a pulley at point B. And through ring A, so this through ring A, and which is attached to a support at point D. Now, knowing that the weight of the container is equal to 1,000 newtons, determine the magnitude of P. So how are we going to determine the magnitude at the magnitude of P? So first, let's try to draw FBD of the pulley at point B. Point B. So we have this now the pulley at point B. So we have this is therefore your P. So that is your P. And okay, it runs over the pulley at B, and therefore this is now via cable AB. So this is now your TAB. It's now your cable TAB. Now, so from here, your TAB is equal to P. Now, you try to go back to the free body diagram. So, we started with spring before, and then next is now your cables and pulley that runs over, okay? The cables that runs over a frictionless pulley to maintain equilibrium. Then, the tension in the cable are equal. Now, similarly, you try to take note that this passes, okay, this passes through a ring at point A. So, we have your of so this is therefore the ring at point A. So this is your TAB. So that one is also equal to your TAB. So this is now your TAB, which is equal to P. And then this is attached to a cable AD. This is now your TAD. Hence, your TAD is equal to TAB, and this one is equal to P. So that one is therefore equal to P. Now, let us try to draw now the free body diagram of joint A. So if you try to draw your free body diagram of joint A. So the free body diagram of joint A. So we have now the weight of the container. So this is the weight of the container, and this is equal to W. So that one is equal to 1,000 newtons. Then we have your TAC. So this is now your TAC. This is your TAC. Tension in cable AC. And then we have the tension in cable AB. This is the tension in cable AB. Tension in cable AB, which is equal to P. And we have the tension in cable AE. This is the tension in cable AE. And also we now have the tension in cable AD. So this one is now the tension in cable AD. So the tension in cable AD is also equal to P. That one is also equal to P. Now, if you try to go over the figure, this is the x-axis. Okay, that is the origin of the coordinate system. So we have the x-axis at this direction, the y-axis in that direction, vertical direction, and this one is now the z-axis. You try to take note in here that whenever you are getting the coordinates of points or the different points, you have to look at the orientation of the axis of the coordinate system. So this point, so we now have a point A. So this is now your point A. So x in there is 0. And then this is now your y. And therefore with this y in here, so we have 1.6. That is the origin. So that is 1.6 below the origin. So we have negative 1.6. And this is the z-axis. So we have the coordinate is 0. Let's proceed to point B. So this is your point B. So the x-axis is 0.78. Negative left of the origin, 0.78. Point B, the y-axis is equal to 0, and the z-axis at point B is equal to 0. So the z-axis is equal to 0. Then we now have your point C. So your point C, we have the x-axis is equal to 0. And then we have the y-axis is, y-coordinate is equal to 0. And we now have the z-coordinate, which is 1.2. So it is forward, so we have positive 1.2. Coordinates of point D. So the coordinates of point D, so in the x-axis, so this is your x-axis, okay, point D, so that is 1.3. So it is positive 1.3. In the y-axis, so it is equal to 0. And we have in the z-axis, which is going in that direction, and this is equal to 0.4 positive, 0.4. Now, for point E, the coordinates of point E in the x-axis. This is your x-axis. So that is now negative 0.4. So it is left of the origin. Negative 0.4. So in the y-axis, this is equal to 0. And we have in the z-axis, so in the z-axis, it is equal to minus 0.86. So that is minus 0.86. Now, let's try to express now the forces as shown in the free body diagram before in Cartesian form. So in Cartesian form. So I'm going to start with W. Okay, you try to look at the free body diagram. So for W, so in Cartesian vector form, your W again is directed along the y-axis, and this is going down. And this one's going down, so it is negative 1,000 J. So in this case, Wx is equal to 0, Wy is equal to negative 1,000 newtons, and Wz is equal to 0. Now, for the tension in cable AC. For tension in cable AC, again, in Cartesian vector form, so this is the magnitude of this vector, multiply this one again by a unit vector in the direction AC. So we have again your unit vector. So let us try to introduce a position vector AC and determine the magnitude of this position vector. So let's try to get now first components again of the distance AC. So we have your X, we have your Y, and the Z component. So that is from A to C. So it's from A to C. So we have C minus A. So that is, okay, so for the X, this is equal to 0. For the Y, 0 minus and minus 1.6, that is positive 1.6. And that is 1.2 minus 0 is 1.2. Hence, your TAC. So we have now your RAC is equal to, okay, X component of the distance is 0. Then Y component is 1.6 J plus 1.2 K. Hence, the magnitude is equal to the square root of 1.6 squared plus 1.2 squared. So this is therefore equal to 2. So that one is equal to 2. Hence, your TAC is now equal to its magnitude times a unit vector AC. That is 1.6J plus 1.2K all over 2. And your TAC in Cartesian form is now equal to, so 1.6 over 1.2 is 0.8. That is 0.8. That is TACJ. plus 0.61.2 over 2 T A C K. So we now have your T A C X, that is 0. Your T A C Y, that is equal to 0.8 T A C. And your T A C Z is equal to 0.6 T A C. So let's now proceed to cable AB. So again, your TAB is equal to the magnitude of this vector, multiply this one by a unit vector AB. So a unit vector AB is now your position vector AB all over the magnitude AB. So again, let's try to get the components of the distance AB, that is from point A to point B. So we have your X, your Y, and then your Z. So that is TAB, so that is B minus A. Okay, B minus A, so we have minus 0.78, that is minus 0, is negative 0.78. And then we have 0 minus and minus 1.6, so that is positive 1.6. And then 0 and 0, so that is equal to 0. Hence, your position vector in the direction AB is now minus 0.78I plus 1.6J. Okay, sa Z component is equal to 0. So that the magnitude is now again equal to the square root of 0.78 square plus 1.6 square. And this is therefore equal to the square root of 3.1684. Now, let's try to determine now your TAB in Cartesian vector form. So your TAB. So it is the magnitude of TAB. Now, if you try to go back to the free body diagram, okay, because it was erased already, your TAB is equal to P. Hence, this is equal to P. Multiply this one by minus 0.78I plus 1.6J over the square root of 3.1684. So we have now your TAB in Cartesian form is now equal to 0.78 over the square root of 3.1684. So that is equal to 0.438 P. So that is I. Plus 1.6 all over the square root of 3.1684. So that is 0.899p. So we have 0.899p. So we now have your J. So in scalar form, your TABX is equal to minus 0.438p. Your TABY is 0.899p. And your TABZ is equal to 0. Now for TAE, that is again equal to the magnitude of TAE. We have a unit vector in the direction AE. So again, your position a unit vector AE is now again a position vector AE all over the magnitude of this position vector. So let's try to determine now the components again of the distance AE. So from point A to point E, so we have E minus A. So that is now your X. We have your Y. We have your Z. So we now have minus 0.4 minus 0, so negative 0.4. 0 minus and minus 1.6 again, so it's positive 1.6. So minus 0.86 minus 0, negative 0.86. So we now have the position vector AE is equal to minus 0.4i plus 1.6j minus 0.86k. So that its magnitude is now equal to the square root of 0.4 square plus 1.6 square plus 0.86 square. And this is therefore equal to the square root of 3 point, the square root of 3.4596. The square root of 3.4596. So that again, your TAE in Cartesian form is your TAE, multiply this one by a unit vector AE, minus 0.4i plus 1.6j minus 0.86k. So that is over the square root of 3.4596. So your TAE is equal to 4 over the square root of this value is 0.215. 0.215 TAEI plus 1.6 over the square root of 3.4596 is 0.86. 0.86 TAEJ minus 0.86 all over square root of 3.4596 is 0.462. 0.462 TAEK. TAEK. And scalar form, your TAEX is negative 0.215 TAE. Your TAEY is 0.86 TAE, and your TAEZ is equal to negative 0.462 TAE. Again, for TAD, again, this is equal to P. So your TAD is equal to its magnitude, multiply this one by a unit vector AD. Again, let us try to introduce a position vector in the direction AD so that we can determine that unit vector, RAD. Now, again, the components of the distance AD. We have your X, your Y, and your Z. So again, the position vector is directed from A to D. So it is D minus A. So it is D minus A. So we have 1.3 minus 0, that is 1.3. 0 minus and minus 1.6, that is positive 1.6. And then 0.4 minus 0. So that is 0.4. So that your RAD is Xi. So we have 1.3i. That is 1.3i. Yj plus 1.6j plus zk 0.4k. Its magnitude is equal to the square root 1.3 square plus 1.6 square plus 0.4 square. And this is equal to the square root of 4.41. Now, so that in Cartesian vector form, your TAD is equal to its magnitude, and its magnitude is equal to P, the magnitude of P. multiply this one by a unit vector AD. So that is 1.3i plus 1.6j plus 0.4k over the square root of 4.41. So that your TAD is now equal to 1.3 over the square root of 4.41, 0.619. 0.619p plus 1.6 over the square root of 4.41, 0.762j plus 0.4 all over the square root of 4.41 is 0.19k. Again, in scalar form, now in scalar form, TADX is 0.619p. TADY is 0.762p. Okay, so we have p in there. So p, j, then plus 0.19p, that is k. And your TADZ is equal to 0.19p. Knowing now the tensions in the different cables, okay, the component in the different cables, let us then apply the equations of equilibrium. So first, summation of forces along the x is equal to 0. And this is equal to your Wx, we have your TACX plus TAEX plus TADX equal to 0. So Wx is equal to 0. TACX is equal to 0. And then we now have your we have TAD muna, ACX, and then we have TABX plus we have your TAE, so we have your X, TACX, TABX, TAEX, and then plus TADY. TADX is equal to 0. So WX 0. So we have TACX is 0. So we have now your TABX. So TABX is negative. Negative. So this one is 0. That one is 0. So we have negative 0.438 P. TAEX is negative. TAEX is negative 0.215 TAE, and then plus TADX. So TADX is plus 0.619P. 619P is now equal to 0. So we have now 0.181P combined these two terms in here, and that is 0.181P minus 0.215 TAE is now equal to 0. Again, that is the first equation. Now, summation of forces along the y is equal to 0. So we have your WY plus TACY plus TABY plus TAEY plus TADY. That is equal to 0. So WY is minus 1,000. That is minus 1,000. Okay. Plus 0.8 TAC plus 0.889P, so that is TABY, plus 0.86 TAE plus 0.762 TADY, and that one TAD is equal to P, and that one is equal to 0. So let's try to combine this P again in here. So we have 1.661 P, 0.8 and 0.76.8. So we have 0.8 plus 0.762. So we have 1.661 P, 0.889 plus 0.762, 1.661 P, and then plus 0.8, that is now your TAC, plus 0.86 TAE is equal to, transpose this to the other side of the equation, 1,000 newtons. Let's consider this one as the second equation. The next equation of equilibrium, summation of forces along the Z is equal to 0. So we have WZ plus TACZ plus TABZ plus TAEZ plus TADZ is equal to 0. Okay, Wj is equal to 0. TACJ is 0.6 TAC. TABJ, that one is equal to 0. And then TAEJ is negative 0.462 TAE. And then we have TADJ is equal to 0.19 P, and that one is equal to 0. So we have 0.19 of P plus 0.6 TAC plus minus 0.462 TAE is equal to 0. Let us consider this one as the third equation. Now, from equation 1, your TAE is equal to 0.181 P all over 0.215. So that is from equation 1. So let us try to substitute this one. Substitute in equation, so let us try to substitute that one in equation 3. So if you try to substitute this in equation 3, so this is our equation 3. So equation 3, 0.19 P plus 0.6 TAC plus minus 0.462 TAE is 0.181 P over 0.215, and this one is equal to 0. Is now equal to 0. Hence, 0.6. So your 0.6 TAC is equal to, let's try to combine this, two terms in here, 0.19P and this term. So that is minus 0.199 of P, 199P, and that is equal to 0. So that your TAC is equal to 0.199 p all over 0.6. So that is over 0.6. Now, again, let's try to substitute TAE in and TAC in equation 2. Okay, let us try to substitute TAC and TAE in equation 2. So this is our equation before. Equation 2. So we have 1.661p plus 0.8. Your TAC is, this is now your TAC, 0.199p over 0.6 plus 0.86. Now, your TAE in here is equal to 0.181p all over 0.215. This was solved using equation 1. And this is equal to 1,000 newtons. Therefore, your P in here is now equal to 377.3 newtons. So that is therefore the